air pollution problems caused by technogenic activity, fires, industrial accidents and other emergency situations, as well as air polluting by chemical and biological objects as a result of terrorist attacks or in the course of military operations, make it necessary to execute precise and prompt monitoring of a noxious cloud release, composition and component concentration, route of advance, velocity, dimensions, as well as predicting its further alterations. The faster the data is received, the more prompt decision is made on further action. Methods that allow obtaining such information are divided into contact and optical spectrum ones. Contact methods have one common disadvantage. They require human presence directly in the area under survey. Optical spectrum methods can also be divided into passive and active ones. Unlike passive methods, based upon object self-radiation receipt and processing, active methods allow not only increasing distance to the surveillance object, but also have broader opportunities on detecting and identifying complex molecular systems. The active methods are based on LiDAR technology application. The word LiDAR, an abbreviation from three English words, light detection and ranging, is coined in the same way as the name of a similar radio ranging technology, radar, and actually stands for laser locator. Application of powerful pulse sources of coherent radiation, such as lasers, allows extending range of standard spectrum methods considerably, and which is more important, using brand new ones designed to define components beyond the reach of the passive methods, biological objects detection in particular. A LiDAR may incorporate several lasers operating in different spectral ranges, video and infrared cameras, as well as incoming data acquisition and analysis systems. In this case, we are talking about a LiDAR complex. In order to have a possibility of prompt delivery of such an installation to a survey area, LiDAR complexes are mounted onto special portable supports, and the fact clears the way to their real-life application. So this demo will expose such a mobile, ground-based application LiDAR complex. We deliberately decided to demonstrate you operation of the two mobile LiDAR complexes, MLC2 and MLC3 at once, as while the complexes are designed for similar task solutions, namely prompt remote aerosol and its chemical composition detection, different constructive approaches have been applied upon their construction, determined by specific clients' requirements. For example, the complexes can be mounted upon dedicated transport modules, whose parameters correspond with the standard 20 feet load conveyors dimensions. In this case, truck chassis designed for container transportation and equipped with a drag-and-draw mechanism enabling transfer of a standalone power supply system included into the complex, serve as a traveling platform. As the complex operation requires accurate azimuth positioning or leveling, the MLCs are equipped with 4 hydraulic supports, outriggers, which are controlled by an onboard computer. Both automatic and manual modes are provided for. With the MLC2, the module is set alongside with the vehicle frame. With the MLC3, the module case is capable of occupying horizontal position independent of the vehicle frame. Such an arrangement allows not only changing or applying various chassis, but also provides for an option for long-distance transportation by railway or air service without chassis. Complex receive-transmit systems rotating scanner can also be executed in various configurations, depending on tasks to be performed. Thus, the MLC2 complex scanner is executed according to the two-mirror scheme, which allows scanning the entire upper hemisphere. While the MLC3 complex is equipped with a sliding assembly, which visual angle is vertically limited by selected sector margins. The MLC2's tilting device is fixed rigidly to the optical plate and is not dismounted in the transportation position, while the MLC3 is equipped with a scanner lifting and lowering mechanism. In traveling position, the scanner is hidden inside, thus reducing the complex dimensions. As mentioned above, the complex operation is based on the principle of atmospheric surface layer laser probing, registration, scattered and reflected radiation processing. Lasers provide active complex operation. Lasers specify multitasking, that is, obtaining data on a number of atmospheric parameters at once. The complex can be equipped with a wide range of radiating elements of various types. These can be ND-YAG lasers, frequency doubling lasers, titanium sapphire tunable lasers, frequency doubling and tripling lasers, and one-mode single frequency tunable TEA-CO2 lasers. Thus, the complex allows performing LiDAR scanning within the following spectral ranges: 230 to 532 nanometers, 750 to 1064 nanometers, and 9 to 11 micrometers. Monitoring pulses output and processing a reflected, scattered signal from the atmosphere is provided by the receive-transmit system. The system includes two-axis scanner telescope, transport optics, light sensors. The receive-transmit system's equipment is mounted onto an optical plate. Rotating scanner with a turning mirror allows monitoring the atmosphere within a wide spatial range, ± 180 in azimuth and ± 15 in elevation. A received signal is processed by the control and data collection system. It incorporates the following: preliminary signal amplifier, analog-digital converters, and an analytical center. Its core is a powerful onboard computer equipped with an ADSP special purpose processor that allows applying original received signal processing algorithms in the real-time mode. It is the computer that executes LiDAR information processing. Air pollutants identification is based upon utilizing both well-established heat-run and original databases, including detailed information on numerous substances absorption cross-section in various parts of the spectrum. Hence, aerosol multi-wavelength LiDAR defines location of natural and artificial aerosol formations in the atmosphere and monitors their evolution. Polarization LiDAR explores their physical structure, being liquid particles, solid crystalline particles, or anything else, and also estimates particles' typical size. Differential absorption LiDAR measures concentration of the gases, which absorption lines coincide with the laser radiation range, and also locates iodine isotopes in the atmosphere, which is crucial for the radiation safety control. For example, in case of nuclear power plants' emergency emissions. Turbulent LiDAR allows estimating turbulence, particles' chaotic motion distribution in the atmosphere in accordance with height. CO2 heterodyne LiDAR determines wind velocity and direction. Mobile LiDAR complex can be equipped with supplementary systems which considerably add to its performance. These can be an infrared radiometer applied to locate fires, explosions, incandescent gas emissions, and so on, and also an infrared high-performance Fourier spectrometer for precise determination of poisonous agents and highly toxic substances of a compound molecular structure by their infrared absorption spectra. Thus, the mobile LiDAR complex allows defining and forecasting further transformation of any substances, including the ones of biological nature. The mobile LiDAR complex also incorporates a video system that allows monitoring and detecting aerosol emissions, defining aerosol cloud azimuth, as well as transmitting this information to the LiDAR system for further analysis. In order to provide video system secure operation, there is applied a special stropped video camera synchronized to the radiating elements operation. While MLC3 is equipped with a single survey camera, MLC2 incorporates a number of cameras. These are wide field, narrow field, and infrared cameras combined into one independent video unit. Received information is displayed in the form of concentration isometric lines on a personal computer's monitor against a background of a digital map of an area being surveyed. Accurate spatial positioning is provided by a GPS receiver integrated into the LiDAR complex. The GPS receiver can be supplemented by special navigation equipment similar to the MLC3 arrangement. The zones where concentration exceeds maximum allowed value are highlighted by a distinguishing color, instantly drawing operators' attention. Information on degree, azimuth, and distance to the pollution area is also displayed on the monitor. At the same time, on operator's choice, LiDAR scanning results can be displayed in any other suitable form. For example, in the form of highlighted areas, each color corresponds with a selected parameter value range. In the form of selected parameter value diagrams of distance. In the form of isometric lines. In order to provide comfortable working conditions for the mobile LiDAR complex operators, an inner climate control system is integrated into it. The fact, as well as individual power supply, makes the complex completely self-sufficient. One can also note that it is also a highly automized system. Being an advanced laser system based upon the most progressive scientific and technological achievements, Mobile LiDAR Complex (MLC) is fitted out with the software meeting all the most up-to-date requirements. MLC's onboard software system provides for prompt and operator-friendly execution of all the operations on setting all the laser, optical, electronic, and electromechanic equipment of the LiDAR complex. It also allows obtaining LiDAR probing results, not only in the form of diagrams and graphs, but also place measurement results onto a base map with the help of a specially developed mapping system. It allows even an operator who doesn't obtain special laser and LiDAR technology-related skills to estimate environmental conditions, locate aerosol clouds, and predict their dynamics, factored in wind and diffusion transfer. By utilizing preset options of testing sets, an operator can select a working mode of the complex, and then the complex is prepared for operation automatically. Next, upon the start command, a corresponding experiment series is performed. An operator has a wide intuitive set of options on various preliminary signal processing, data averaging, smoothing and standardization, background subtraction, presenting digital data in a more human-readable format, as well as any combination of various signal processing methods. It allows obtaining a moving cloud image, carrying information on various physical parameters, predicting aerosol clouds propagation and monitoring various air formations movements with surrounding landscape reference. MLC operator acquires all the data necessary to make a decision: current cloud position, concentration pattern in a base map in the form of isometric lines, wind velocity and direction, and which is more important, a forecast of a cloud position and prediction of concentration patterns. So, having examined mobile LiDAR complex performance capabilities, let's specify the scope of its application. The system is capable of providing continuous monitoring of a city's atmosphere condition and defining pollutants concentration, highly toxic and poisonous substances, locating the place, source, origin, and development dynamics, with further placement of the survey results onto a base map, and storing obtained information both as video record and as LiDAR analysis results. It is especially relevant to apply mobile LiDAR complexes upon emergency situations, both natural and industrial. Fires, explosions, emergency emissions at chemical and nuclear power plants, Automized remote system for major industrial centers operation monitoring is capable of prompt accident detection in an automatic mode, and it secures information support for the emergency rescue services actions in an accident area. The LiDAR complex allows for accurate measurement of the parameters, specifying an accident area and realization of maximum allowable concentration isometric lines in dynamics. The LiDAR complex is capable of providing long-term meteorological conditions monitoring, measurements of wind velocity, atmospheric turbulence, cloud structure, and air humidity. One of the LiDAR complex scopes of application is general ecology. Atmospheric strata processes monitoring, measurements of tropospheric and stratospheric ozone and aerosols distribution and interaction, aerosol and ozone correlation. And finally, it is a wide scope of special solutions. MLC2 and MLC3, as well as already delivered MLC1, have been designed and produced by the research and production enterprise Laser Systems. And as you can see, though the missions they are designed for have much in common, the complexes themselves are different. The one is oriented towards our native country. The other is supplied abroad, where the research and production enterprise Laser Systems has been duly respected for a long time already. Each new complex, produced by the research and production enterprise Laser Systems specialists, has been created with due account for individual requirements of each particular client. Every complex is refined during field testing, which is carried out in collaboration with the client's representatives. And in the meantime, Laser Systems developers are working on a new generation of mobile LiDAR complexes, as well as other products, such as extra-atmospheric optical monitoring systems, as there are still tasks that require even more advanced and superordinary solutions.